On the 22nd of May, 2026, SpaceX launched the most powerful rocket ever built for the 12th time. And this one was supposed to be different. This was Starship version 3, a ground-up redesign. The Raptor 3 engine, advertised for 2 years as SpaceX's answer to every reliability problem Raptor 2 ever had, a simplified architecture, higher thrust, fewer parts, more survivability. The stack was Booster 19 and Ship 39. The pad was the newly commissioned Pad 2 at Starbase, itself a statement about SpaceX's industrial ambitions. 2 orbital launch complexes. Simultaneous vehicle processing. This was supposed to be the flight where Starship stopped looking like a test program and started looking like a launch vehicle. 1 minute and 42 seconds into ascent. Engine out. One of the 33 Raptor 3 engines on Booster 19 shut down unexpectedly. Not a catastrophic failure. Engine out tolerance is built into Starship's design philosophy from the beginning. Losing one of 33 is in principle survivable. The vehicle continued climbing, then came stage separation. Everything up to this point was nominal. The upper stage lit, 6 Raptor engines ignited. They pushed Ship 39 upward toward space. The mission, from the perspective of the upper stage, was largely intact. But below in the booster, something was already going wrong. The boostback burn is the maneuver that takes a 70-meter column of steel traveling at hypersonic speed and redirects it, not just slowing it down, but reversing its trajectory, aiming it back toward its recovery zone in the Gulf. It is not an edge case. It is not an optional maneuver. Every operational Starship profile in SpaceX's plans, for Starlink, for crewed flight, for Mars, depends on a booster that can execute a boostback burn reliably. This one could not. SpaceX's webcast showed it in real time. On-screen graphics indicated 12 of 13 center engines ignited at the 2-minute 32-second mark. Then the outer ring began attempting to relight, and several indicators showed engines that simply were not responding. SpaceX's communications lead on the webcast said the words plainly. We are not seeing as many booster engines ignited as we expected for boostback. According to SpaceX's own post-mission report, the company's own words, Booster 19 was unable to light all planned engines and performed a partial boostback burn that ended early. The burn lasted less than 20 seconds. It was scheduled to last approximately 60. The booster never built enough thrust to reverse its trajectory. It continued downrange. It attempted a landing burn. That failed too. And then a hard splashdown. Not a controlled water landing. An impact. The SpaceX commentator watching the data said it simply, "Looks like the booster's coming in hot." Contact was lost. Recovery operations were called off. Now, here's why this matters beyond the hardware. The Raptor 3 engine didn't lose one unit randomly during ascent. It lost multiple units in quick succession during a planned and choreographed maneuver. A maneuver it was specifically designed to survive. That is a categorically different problem from a random single shutdown. That is a pattern. And patterns point towards systemic failure modes, not bad luck. Let's talk about the engine. Raptor 3 is a full-flow staged combustion engine. What that means in practice is that every gram of propellant, both methane fuel and liquid oxygen oxidizer, passes through pre-burners before reaching the combustion chamber. This makes it extraordinarily efficient. It also makes ignition extraordinarily complex. The startup sequence involves dual pre-burners firing in a specific tightly timed choreography. Dual turbopumps spinning up in precise synchronization. Propellant flows that must be balanced to within milliseconds. Elon Musk himself acknowledged this publicly before Flight 12, describing the Raptor 3 startup as requiring insane timing precision to avoid engine failure. On Flight 12, during a high-stress boostback maneuver with the booster flipped, engines cold-soaked, propellant under different gravitational and dynamic conditions than during ascent. Several engines failed to light cleanly almost immediately after ignition. The booster never had a chance. And it wasn't only the booster. Ship 39, the upper stage, also lost one of its 3 Raptor vacuum engines during ascent. The flight computer compensated brilliantly, gimballing the remaining engines and extending the burn time to reach the planned trajectory. But the ship arrived in space with nearly depleted propellant margins. SpaceX mission controllers made a real-time decision: cancel the planned in-space engine relight, cancel part of the re-entry test, take the controlled Indian Ocean splashdown and call it a mission. The ship survived. Most of its objectives were met. Payload deployment worked. 20 Starlink mass simulators, plus 2 modified satellites equipped with external cameras, successfully deployed from the new PEZ dispenser payload bay. But the booster, the half of Starship that makes the economics of the whole system work, was gone. 5 days after Flight 12, on May 27, 2026, the Federal Aviation Administration issued a statement. The Flight 12 launch, it said, had resulted in a mishap. Those two words triggered a formal process with real consequences. Under federal regulations, specifically 14 CFR Part 450, the FAA must initiate a mishap investigation whenever specific thresholds are crossed. Those thresholds include hazardous debris landing outside defined areas, failure to complete a launch as planned, or malfunction of a safety-critical system. Flight 12 crossed multiple thresholds. The booster's uncontrolled descent prompted the FAA to activate a debris response area over the Gulf. 5 aircraft were placed in holding patterns. 6 departures were delayed. No one was hurt. No public property was damaged. But that is not what determines whether a mishap investigation happens. It happens whenever the vehicle fails to do what the license says it will do. And this one did not. The structure of the investigation matters. This is not the FAA conducting its own inquiry into SpaceX. The law requires SpaceX to lead the investigation itself, but the FAA is, in the agency's own words, involved in every step of the process. SpaceX must submit a final report. The FAA must approve it, including any corrective actions, and until that approval is granted, Starship does not fly. This is not new territory for SpaceX. Every one of the first 4 integrated Starship flights ended in a mishap investigation. Flight 7, in January 2025, saw Ship 33 break apart over the Caribbean. Flight 8, in March 2025, lost Ship 34 less than 9 minutes after liftoff, traced to a hardware failure in a Raptor engine center section, causing inadvertent propellant mixing and ignition. The Flight 8 investigation was only closed in June 2025 after over 100 long-duration Raptor firings at SpaceX's McGregor test facility. Flight 12's investigation is the first for version 3, and it arrives at a uniquely pressured moment. 2 days before Flight 12 launched, SpaceX filed its public S-1 prospectus with the Securities and Exchange Commission, an IPO targeting the NASDAQ under the ticker SPCX. An IPO roadshow expected to begin around June 4, 2026. Shares potentially beginning to trade as early as June 12th. SpaceX's growth story, the revenue narrative that underpins its valuation, depends substantially on Starlink, and Starlink's next generation, version 3, requires Starship to fly. Those satellites are designed exclusively for Starship. SpaceX said in its EOS-1 that it aims to begin deploying Starlink V3 in the second half of 2026. Every week that Starship sits grounded is a week that timeline slips, and investors are watching. Here's what SpaceX's investigation must determine and report to the FAA. First, the root cause of the multi-engine failure during the boostback burn. Not just which engines failed, but why multiple Raptor 3 engines, in their first operational flight, failed to achieve stable ignition during a maneuver they were designed to execute. Is this a fuel delivery problem? A timing issue in the startup sequencing software? A cold soak sensitivity unique to the boostback configuration, where engines that were running during ascent are shut down, left in freezing conditions, and then asked to relight cleanly? Is there a systemic design flaw in the Raptor 3 ignition architecture? Second, the cause of the RVAC engine loss on the upper stage. Was it related to the same class of issue, or an independent failure mode? Third, whether the corrective actions SpaceX identifies genuinely eliminate the failure mechanism, not just patch around it. The FAA does not have to wait for the full investigation to close before allowing a return to flight. It did exactly that after Flight 7, clearing Flight 8 to launch before the Flight 7 inquiry was complete. After determining that the specific failure mode from Flight 7 did not pose a public safety risk to Flight 8, it could do the same here. But the precedent from Flight 8 also carries a warning. A regulatory clean closeout is not the same thing as a clean return to flight. Months after Flight 8 was cleared and flew, the pattern of Raptor engine failures continued, precisely the pattern Raptor 3 was supposed to solve. The question the investigation must answer isn't just what broke. It's whether SpaceX truly understands why, and whether Flight 13 will reflect that understanding. Flight 13 hardware, Booster 20 and Ship 40, was already in preparation at Starbase before Flight 12 even launched. That's not unusual. That's the SpaceX model. Parallel processing, simultaneous vehicle flow, industrial tempo rather than careful sequential testing. Ship 40 was fully tiled with its thermal protection system before Flight 12 flew. Booster 20 had already been through static fire preparations. Though notably, SpaceX transferred at least 10 Raptor engines from Booster 20 to Booster 19 after a 10-engine static fire of Booster 20 ended abruptly due to a groundside issue in March. Booster 20 was effectively cannibalized to make Booster 19 flight ready. Now Booster 20 needs engines. And those engines, in light of Flight 12, need to be engines SpaceX understands. Before Flight 13 can fly, SpaceX will need to conduct a full multi-engine static fire of Booster 20, and this time with the specific goal of validating the boostback ignition sequence under realistic conditions. That is not a trivial test. It requires the booster to be on the launch mount, engines cold-soaked, propellant loaded, and the ignition timing sequencing tested against the exact conditions the boostback burn failed under on Flight 12. NASASpaceFlight has reported a likely July to August 2026 window for Flight 13, pending that testing and any mitigation efforts. And what does Flight 13 actually attempt before Flight 12 flew? The picture was ambitious. Every version of Starship that exists today was built on the wreckage of a previous anomaly. It's a statement about what iterative development at this scale actually looks like. Flight 13 is the next iteration. The booster will roll out, the engines will be loaded, the countdown will run. And somewhere in the ignition sequence, in those first milliseconds when 33 Raptor engines are asked to wake up and push the world's heaviest rocket into the sky, the answer to the question Flight 12 raised will begin to form. We'll be watching. If you've made it this far, you understand why this flight matters more than the headlines suggest. Most coverage called Flight 12 a partial success and moved on. The engineering story is more complicated than that, and Flight 13 will be the real test. Subscribe if you want the breakdown when it happens. We cover the parts everyone else skips.